Good morning. Now, today onwards, we are going to discuss about a new module, which is the digital electronics. Especially in this module, we will discuss about the basic logic gates, namely the AND gate, OR gate, and NOT gate, and also about the different other gates like NOR gate and NAND gates. Also, we will discuss about some of the laws regarding the logical gates, namely the De Morgan's theorems. Also, we will discuss about the half adder, full adder, and flip-flops in this module. In this video, we will try to introduce the basic logic gates or the basic circuit which may be familiar to you, namely the NOT gate, the voice called the inverter, the OR gate, and AND gate. As you know that a digital circuit having one or more input signals but only one output signal is called a gate. So gate is a digital circuit having one or more input signals and one output signal. The basic gates are NOT, OR, and AND gate. These three gates are treated as the basic gates because connecting these basic gates in different ways makes it possible to produce circuits that perform different arithmetic and logical operations. Because these gates can be used to simulate mental processes, these gates are often called logic circuits. The gates are otherwise called logic circuits or logical gates because they can produce or they can simulate the mental processes. But in this chapter, we will try to discuss only about the logical circuits, not how these mental processes can be simulated using the basic logic gates. So in this video, we will mainly concentrate on introducing the basic logic gates or the fundamental logic gates, NOT gate, OR gate, and AND gate. They are called basic logic gates or fundamental gates because using these gates we can produce all other gates or all other circuits that perform different arithmetic and logical operations. So now let's discuss about the different basic gates separately. First of all, we will discuss about the NOT gate. While discussing a particular gate, the important things which we will try to introduce here is its symbolic representation, the symbol used to represent that particular gate. Then we will discuss about the truth table. Truth table is actually a table which contains the output of the logic gate for different combinations of the input signals. And this we will consider the operations on binary number system. So we will have the inputs as either 0 or 1. Then we will have to discuss about an expression which represents the output of this particular gate in terms of the input. So we will have a particular symbolic representation or a particular sign to represent that logical operation, and in terms of that sign we will express the output as an equation or expression in terms of the input, which is called the Boolean expression. So we have to discuss about the Boolean expression, and finally we will discuss about the IC, which give us the or which actually consisting of this particular logic gate. So it's IC pin number and its pin diagram. IC number and pin diagram are we are going to discuss for that particular gate. So these four things which we will discuss for each basic gates. That is the symbolic representation, the truth table, which gives the a table consisting of the output for different combinations of the input, then the Boolean expression, the expression connecting the inputs and output, and the IC, which consisting of that particular logic gate whose pin diagram and the IC number. So first of all, consider the NOT gate. NOT gate is otherwise called an inverter because it is having only one input and one output. The output is always the complement of the input, or the inverted, we are getting an inverted input or inverter of the input, or the output will be the inverted or the complement of the input. So if you consider the input as 0, then the complement of 0 is 1 in the binary system, and if you consider 1, then its complement is 0. So this is the logical operation performed by a NOT gate. So NOT gate is a digital circuit with one input and one output, with the output is the complement of the input, or input is inverted in the output, which is a NOT gate. The symbolic representation of a NOT gate is given by like this: a triangle with a circle at one end and one input terminal and one output terminal. The input is usually represented by A, the output is usually represented by Y, and Y is always the inverted or the complement of A, so usually represented by A bar. Now if you consider the truth table is a table which contains the output of that logic gate for different combinations of the input. So we need a table which consisting of the inputs and outputs. Here the input is only one, so it is A, and the output is Y. For different combinations of input, the possible combination for input with a single terminal, input terminal, are either A equal to 0 or A equal to 1. When A equal to 0, the complement of this one, that is output, will be 1, that is A complement, and when input is 1, the output will be 0. Now the Boolean expression is the expression relating the input and output, that is why the output is always equal to A complement. Usually some others will use the representation A prime to represent the complement, or sometimes they explicitly write not A. These are the different representation for representing the complement. So in this video or in these lectures, I will use this convention, the bar, to represent the complement of a logical input. So y is equal to a bar, which is read as actually y is equal to a complement, is represented by putting a bar over that particular input. So this is the Boolean expression for the NOT gate. Now regarding the IC and the pin diagram, the IC 7404 is a logical NOT gate IC, which is a integrated chip with 14 pins. So if you consider a 14 pin 7404 IC, it will have 14 pins. So suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. All are so always all digital ICs will have certain pins for plus VCC and ground. Here the pin number 7 is grounded and 14 is plus VCC. For this one it is plus 5 volt. And pin number 1 and 2 we are having the first gate. So this is a gate, first logical NOT gate. Pin number 1 is the input and pin number 2 is the output. The second gate is between the pin numbers 3 and 4. 3 is the input, 4 is the output. The third is between the pin numbers 5 and 6. 5 is the input and 6 is the output. Now the next logical gate is between the pin numbers 8 and 9. 8 is the output, 9 is the input, and it is 10 and 11. 10 is the output and 11 is the input. Now next gate is like this. 12 is the input and 13 is the output. So this is the IC 7404. To identify the pins 1, 2, etc. of the IC, if you take an IC, you can see that there is a dip or a cutting at one end of that IC. Hold the IC in your hand in such a way that this tip is towards your left. Then the downward pins are starting from left are 1, 2, 3, etc. up to 7, and in the other end, top end, from right to left you can have the pin numbers 8, 9, 10, etc. up to 14. Out of this, the pin number 7 is the ground terminal and pin number 14 is the plus VCC. So to check the logical gate operation of different gates, first of all you have to connect the ground of the power supply to the terminal 7 or to the pin 7 and plus 5 volt of the power supply to the pin number 14. Then apply different logical values, either the 0 input or high input. That is, for a 5 volt power supply you can apply 0, the ground to 1, or you can apply 5 volt to 1. then the corresponding outputs may be noted. When 1 is 0, then 2, the output terminal will show high value, that is 5 volt. When 1 is 5, then output 2 will show 0. Similarly for all other gates. So this IC 7404, which is a NOT gate logical IC, will have 6 gates in it, 6 NOT gates in it. Each gate is having one pin for input and one pin for the output. So this is the IC pin diagram of the IC 7404. The IC pin diagram is needed for you to do the practicals. So this is also helpful for your doing your practical. So always remember these things: the symbolic representation of the IC, the gate, the truth table of the gate, the Boolean expression, and the IC number and its pin diagram. Now the next gate is the OR gate. OR gate is a digital circuit with 2 or more input signals and one output signal. The output will be high when any one of the input is high. So if any one of the input is high, the output of the OR gate will be high. So the symbolic representation is given by like this. So some curved this is a 2. If you consider the 2 terminal, 1 terminal and 2 terminal input, the inputs are A and B, the output is Y. So this is the symbol representing the OR gate, logical OR gate. Now if you consider the Boolean expression, to get the Boolean expression we need a logical sign to represent this logical operation. The OR gate logical operation is represented by the mathematical symbol plus. That is, if A and B are the inputs, the output is A or B. It is actually read as A or B, not A plus B. So always try to read like Y is equal to A or B. So this is the Boolean expression. Y is equal to A or B is the Boolean expression for the OR gate. Now if you consider the truth table, it will have 2 inputs A and B and one output Y. So let's see what are the input values for different combinations of the input. Since we are considering a 2 input signal, the different combinations are or possibilities are either A is 0, B is 0, or A is 0, B is high, or A is high and B is low, or both the inputs are high, or 1 1. So when A is 0, B is 0, both the inputs are low, so the output of the OR gate is 0. When A is 0, B is 1, the output of the OR gate is high. When any one of the input is high, so it will be 1. Here also it will be 1. When both the inputs are high, then output will also be 1. So this is the truth table for the OR gate. This is the Boolean expression expression. This is the symbol. Now the IC 7432 is a logical OR gate IC. It is also a 14-pin IC. If you consider the pin diagram of this IC, which actually consisting of 14 pins, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Here also you can see a cutting at one end. Hold this to your left side, then count from the left. This is 1, this is 2, this is 3, 4, 5, 6, 7, and 7 is the ground terminal of this IC, and this is 8, 9, 10, 11, 12, 13, 14. 14 is the plus VCC, which is usually plus 5 volt. Now the first OR gate is between the pins 1, 2 and 3. The 1 and 2 are the input and 3 is the output. Second OR gate is between these 4, 5, 6. 4 and 5 are the two input terminals and 6 is the output. Then third logical gate is having the pin number 8 as the output and 9 and 10 as the input terminals. Then fourth logical gate is the pin number 11 as the input and output, and 12 and 13 as the output. So this is the IC 7432. This is the pin diagram of the IC 7432. It consisting of 4 logical OR gates with 3, 6, 8, 11 as the output pins for each gates, and for the first gate 1 and 2 are the input pins, and pin number 4 and 5 are the input pin for the second gate. Pin number 9, 10 are the input for the third gate, and pin number 12, 13 are the input for the fourth logical gate. So this is the pin diagram of IC 7432. So IC 7432 is a 2-terminal input logical OR gate IC, which consisting of 4 logical OR gates in it. The pins 7 and 14 are for ground and plus VCC or 5 volt respectively. Now I told you in the beginning that OR gate is a digital circuit or a logical gate with 2 or more input and 1 output. Here we are discussed only about the 2 input. So we can have more inputs. That is, if you are having a 3 input logical OR gate, then the symbol will be like this. 1 output, that is Y, which is equal to inputs. Suppose we are having 3 inputs, namely A, B and C. Then output will be Y is equal to A or B or C. This is the Boolean expression. The truth table you can see like this: A, B, C and Y. The different combination of A, B, C or A, B is equal to 0, then Y is equal to 0. When A, B are 0, C equal to 1, you can have Y is equal to 1. When 0 is 1, 0, you can have 1 output. When 0, 1, 1, you can also have again 1 output. Then the other combination is A is equal to 1, B equal to 0, C equal to 0, then still again Y is equal to 1. 1, 0, 1, output is 1. 1, 1, 0, output is 1. 1, 1, 1, output is again 1. So for a 3 terminal input OR gate, the output Y is 0 only when all the inputs A, B, C are 0. And for all other combinations of A, B, C, the output Y is high. So this is the truth table for a logical OR gate with 3 input terminals. So you can see that Y is equal to 0 only when when all of the inputs are 0, and output Y is high when any one of the input is high. So that's all about the logical OR gate. Now let's discuss the last basic or fundamental gate, that is the AND gate. AND gate is a logical gate or a digital circuit with 2 or more inputs and 1 output. The output of AND gate is high only when all inputs are high. So only when all inputs are high, the output of the logical AND gate is high. The symbol is like this, a bar with a curve like this. It almost resembles exactly like the English alphabet, the D. Don't confuse with the OR gate. OR gate is having a symbol like this, a curve, then a pointed curve like this. But here it is a curved one and a straight bar. So it almost looks like a English alphabet letter D. So here suppose the inputs are A and B, 2 input logical AND gate. The output is Y, and the logical operation of AND is represented by the symbol dot. So this is A and B. This dot is actually read as AND. So this is read as Y is equal to A and B is the symbol. This is the symbol representing a logical AND gate, and the Boolean expression is this one, Y is equal to A and B for 2 inputs A and B. Now if you consider the logic truth table, suppose we can have 2 inputs A and B, the output is Y. Now usually it should be represented by a table. Always try to write like that. And also here when you write Y, always write what will be the output, that is Boolean expression. Now suppose consider the different combinations of A and B. A, B, 0, 0, 0, 1, 1, 0, then 1, 1. And the output of AND gate is high only when both the inputs are high. Here both the inputs are low, so output is 0. Here one of the input is 0, that is A is 0, so output is 0. Here also B is 0, that is one of the inputs, so output will be 0. Then here both the inputs are high, so output will be 1. So this is the truth table for a logical AND gate. Now, if you consider the IC 7408 is the IC which represents the logical AND, or the IC 7408 is a logical AND IC. It is also a 14-pin IC. If we consider the pin diagram, you can see 14 pins 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The pin number 14 is actually VCC, that is 5 volt. Here you can see a cutting. This is 1, this is 2, this is 3, 4, 5, 6, 7. 7 is actually grounded. Then 8, 9, 10, 11, 12, 13. The first AND gate is between the 3 pins 1, 2, 3 with a 3 as the output and 2 and 1 as the input. 4 and 5 as the input and 6 as the output for the next gate, and 8 as the output and 9 and 10 as the input. Then 11 as the output and 12 and 13 as the input for the last gate. So this is IC 740. It also consisting of 4 logical AND gates. The 7 and 14 are the ground and plus VCC respectively. So this is a 7408 is a 2-terminal input logical AND gate IC consisting of 4 logical AND gates. The Boolean expression for the AND gate is given by this expression: y is equal to a and b. The truth table for a 2-terminal input is given like this. For a 3-terminal input, the output y is 1 or high only when all the inputs are high. That is, if a, b, c are the inputs, then only when a equal to 1, b equal to 1, c equal to 1, y will be 1, and for all other combinations of a, b, c, the output will be 0. So that's all about the logical AND. So this completes the 3 basic logic gates or fundamental gates, because they are called basic gates, because using these gates we can construct all other gates or different logical circuits that can perform different arithmetic operations or different logical operations. So these are the basic gates or fundamental gates, not, or, and gate. So they are called basic gates because by connecting these gates in different ways makes it possible to construct different circuits that perform different logical operations. Now in the next video onwards, we will discuss about some of the different circuits which can construct by using these basic gates, and about different theorems which enables us to simplify some complicated or large digital circuits into the simplified form. So that's all about these fundamental gates. Thank you.